It is recalled that the stability of each nuclide is based on the equilibrium and good distribution of the masses in relation to the principles of geometrical symmetry. For example, in the series of elements of the fourth dodecahedral layer, the additions are made by groups of 6 pentagons in the crown. It is therefore a large mass plated on the nuclear wall.
Thus, a single addition leads to a disturbing imbalance. Conversely, an addition of 19 crowns also leads to an imbalance by the absence of the 20th surface addition. This is why elements 43, technetium, and 61, promethium, are unstable and do not exist in nature because they are too unbalanced.
On the other hand, there is always at least one stable isotope in each of the elements of the dodecahedral layers thanks to a good distribution of the masses. Now, the abundance of isotopes will then depend on the position of the pentagonal additions according to the geometry of the 20 dodecahedral peaks.
Under these conditions, an obvious property symmetry can be seen between the first 10 wall additions and the subsequent 10 additions of each dodecahedral layer. We have just pointed out that the elements 43 and 61 of the fourth layer are unstable because the additions 1 and 19 on the 20 vertices are too unbalanced.
On the other hand, stability is optimal when the parietal additions are distributed along the summits of platonic solids. Thus, with 4 additions depending on the tetrahedral peaks, we then have a good balanced distribution. We then find selenium-34 with 5 stable isotopes on the third layer. Then the palladium-46 with 6 stable isotopes on the fourth layer. And dysprosium-66 with 7 stable isotopes in the fifth layer.
In tetrahedral symmetry, that is to say with 4 absences of additions, we have zirconium-40 on the third layer with 4 stable isotopes. Then cerium-58 for the fourth with 4 stable isotopes. And palladium-78 on the fifth layer with 5 stable isotopes.
With 8 additions on the 8 vertices of the cube base, we obtain the most balanced morphology for the dodecahedral layers. This leads the elements with 8 parietal additions to develop the most stable isotopes. Thus, we have krypton-36 for the third layer with 6 stable isotopes. Then it is the tin-50 for the fourth layer, which is the element which has 10 stable isotopes. That is to say the maximum of the universe. And it is ytterbium-70 in the fifth layer with 7 stable isotopes.
Similarly, in the absence of 8 parietal gaps, we find this morphological equilibrium. Strontium-38 has 4 stable isotopes in the third layer. Xenon-54 exhibits 8 stable isotopes in the fourth layer. And tungsten-74 contains 4 stable isotopes in the fifth layer.
With 6 parietal additions we arrive at an octahedral distribution. In fact, cadmium-48 has 8 stable isotopes in the fourth layer. And erbium-68 has 6 stable isotopes in the fifth layer.
In contrast, with 6 parietal absences we find the barium-56 with 6 stable isotopes in the 4th layer, and osmium-76 with 6 stable isotopes in the 5th layer.
Now, with 2 opposing parietal additions, we find ruthenium-44 with 7 stable isotopes in the 4th layer, and gadolinium-64 with 6 stable isotopes for the 5th layer.
On the other side, with 2 absences in opposition we find the neodymium-60 with 5 stable isotopes in the 4th layer, and we have mercury-80 with 7 stable isotopes in the 5th layer.
Now, with 10 parietal additions, one can have 2 types of distributions. The first in bipolar position is with twice 5 additions in opposition,
and another is an equatorial distribution with 10 additions.
For the 4th layer we have tellurium-52 with 8 stable isotopes, and for the 5th layer we find hafnium-72 with 5 stable isotopes.
On the other hand, it is observed that the 3rd dodecahedral layer shows a higher stiffness due to its small size, because the base parietal additions 2, 6, 10, 14 and 18 comprise only 1 or 2 stable isotopes. But on the whole we can see the effects of pentamorphy. We have indeed a correspondence of structural properties between the first additions of the layers and their symmetry of the parietal gap. Moreover, additions of odd number can contain only 1 or 2 stable isotopes because the non-Platonic distribution imposes a very limited balance and counterweight to compensate.
This is also true in the 4th layer with the additions in position 3, 5, 7, 9 and their symmetry at 17, 15, 13 and 11. The most symbolic is the technetium and promethium pair of the 4th layer in position 1 and 19. With the 5th layer, these same penalties are found for nuclides with an odd number.
However, since additions of pentagons are made by pairs, there are no prohibited cases for additions 1 and 19. Now, it can be confirmed that the additions of Platonic distribution favor the existence of numerous isotopes. This is the case for additions of 8 in cubic distribution with a maximum for 10 with 10 isotopes. It is then the tetrahedral distribution in 4 additions or 4 gaps. It is also the octahedral distribution with 6 additions or 6 gaps.
Again in the 4th and 5th layers, the 2 additions or gaps in oppositions favor the presence of stable isotopes. Finally, the 10 additions also offer the possibility of providing stable isotopes.
T for 2 and 2 for T, just me for you and you for me alone. Nobody near us to see us or hear us, no friend